slides properly?
Yes.
Yes, we do.
Very well. So we're going to switch gear a little bit here. The previous presentation focused on means to decarbonize the electric grid. I'm going to introduce a new low carbon energy technology that has the potential to help decarbonize all sectors of the economy, which account for the other sectors of the economy, which account for roughly 75% of the carbon emissions. But the name of that technology is nuclear batteries, and I'm going to introduce it in in a few minutes. But first, let me start with some big picture comment, if I can move through the slides here. So the magnitude of the challenge facing humanity, the challenge associated with dealing with climate change is, as we know, very, very severe. And I think there is emerging consensus that an all of the above technology approach is the right way to go. Tyler's analysis certainly shows the value of firm capacity. In the United States in particular, there appears to be growing support for the first time in many years for nuclear energy to play a big role in a low carbon world. The support comes from a variety of sources, some more surprising than others. I'd like to start by pointing out to climatologists, including Ken Caldera, collaborator of the previous speaker, as well as MIT's own Kerry Emanuel. They are on record for claiming or calling for a substantial role of nuclear power in the overall climate stabilization effort. Nuclear also enjoys support across both aisles or sides of the aisle in Washington, D.C. A couple of quotes at the bottom of the slide from the previous energy secretary, a Republican, the current energy secretary, a Democrat. Captains of industry and opinion makers or opinion leaders, I should say, like Bill Gates, have personally invested and very publicly stated that nuclear has to be part of the solution. And then also historically, nuclear skeptical organizations such as the Union of Concerned Scientists have come out calling for nuclear to continue to play a role. In particular, the focus for them is the existing fleet, which in the United States accounts, the existing fleet of nuclear reactors, which in the United States accounts for over 50% of our carbon-free electricity currently. There is also a significant interest in new nuclear technologies with support from private capital, and this is also a fairly new phenomenon, if you wish. Traditionally, the development of new nuclear technology has been driven by the Department of Energy, by government money. That still remains the case, but now it's been accompanied by a robust influx of private capital. In North America, US in particular, but also Canada, there are currently 70 advanced nuclear technology projects. I want to be clear, not all of these are equally credible in terms of technical capabilities. There is certainly a wide range of reactor types, including fusion. Some are more near term, some are longer term, but it points to the sort of the support and at a minimum the interest for this set of technologies. If I were to quantify, I would say that roughly a dozen, maybe a little bit more of these projects are serious, and maybe 1/3 of those are very likely to see commercialization in the near future. You're not expected to read this slide. It's just to give you an idea of the wealth of enacted legislation and other government initiatives at the federal and state levels, as well as regulatory initiatives that are meant to support new nuclear in the US, existing and new nuclear. And again, all enacted legislation about new nuclear has been supported in a bipartisan fashion in the United States. Okay, well, so if nuclear is to play a big role going forward, what is the expected business model by which nuclear should play? And if you look at the traditional business model, is based on a very lengthy, sort of a decade-long testing and licensing process for new nuclear technologies that come to market, an equally long construction period for very large gigawatt-scale plants, which ultimately are connected to the electric grid. And the combination of these four features is what I call the perfect storm of negative attributes. It takes a long time These are big projects, multi-billion dollars, and when they're done, they're connected to the electric grid, which is sort of the ultimate commodity market. So there is no added value for the product that is generated by these nuclear plants. And I would argue that that traditional business model in places like the United States and Europe has become economically very, very unattractive. Now, let me be clear, there are very important regions of the world, I'm thinking China, Korea, India, Russia to an extent, and the Middle East, where this traditional business model based on large plants is still quite successful, because essentially there is a cadre of companies, particularly East Asian companies and also India and Russia, that have been building new nuclear power plants continuously over the past 20 to 30 years. They have a very good know-how, and they can deliver these large machines, these large plants, on budget and on schedule. But in the US and Europe, recent examples clearly show that our industry has lost that ability. And so I advocate for a 180-degree shift in the nuclear business model or in the nuclear deployment model. And this shift entails much smaller and more serially manufactured systems that don't look like big construction sites. And I'm going to elaborate on that in just a minute. We've accelerated testing and licensing, not decade long, but more like half a decade or maybe even shorter than that. And then possibly producing energy products that are not just commodity, but they command a premium in markets. And for that, you need to look at electricity, not necessarily on the grid, but also heat, hydrogen, desalinated water, and so on. And I'll elaborate on this as well. So keep in mind those three sort of elements of that new paradigm, and now we're going to discuss this one at a time. Smaller machines, I think the industry in the US particularly gets this, and so the trend is definitely to go towards smaller machines with a lower number of nuclear system structure and components, and therefore lower complexity. This just per se reduces the cost and time for designing and engineering a nuclear power plant. And it also quite dramatically could reduce the cost and the schedule of that all-important first demonstration project, which ultimately is going to set the tone for the series of additional units that are going to be built after that, as well as the first of a kind commercial. So let's quantify these numbers a little bit more. A traditional large gigawatt scale light water reactor produces roughly 1,000 megawatts, and sometimes even more, 1.5, 1.6, very large machine, can take order of $10 billion. Again, these are costs in the West. In China, in Korea, they routinely come in with a third of this cost, but that's what we've seen in the West, and it takes a decade. Very, very big, very long projects. There is a new class of reactors that people are excited about. They're called small modular reactors. They're essentially shrunk or miniaturized versions of these traditional technologies. They use the same fuel, the same cladding materials. A lot of the components look the same, but they're smaller in size, so the system is simplified. It still requires substantial civil works, and so in some ways resembles a traditional construction project. But the order of magnitude of the investment here is expected to be more like $1 billion. So you're down an order of magnitude, which certainly in terms of reducing the financial risk is good news. And the expected completion time would be order of 5 years. The power output for these systems could be between, say, 100 and 300 megawatts. So again, you're down by a factor of 10 roughly in power output. And what I'm going to focus on today is the last category that you see here on the right. And these are microreactors. I'm going to tell you what I mean by nuclear battery, but essentially the same thing. These microreactors are now systems in which you've gone down an additional order of magnitude, both in terms of power output as well as physical size. I'll show you in the next slide what that really means. The implication of this, based on cost analysis that not only our group at MIT, but other folks in the community are doing, is that the initial investment for construction of one such system could be, for the first of a kind, it could be of the order of $100 million, maybe even less, and it would take less than 3 years actually to entirely build a factory. So what is the nuclear battery? Well, it is a microreactor, so it's a nuclear reactor. It generates between, say, 1 and 20 megawatt. It really depends on the design of heat and electricity. Nuclear reactors are heat sources, and then in order to produce electricity, you need to attach it to a power conversion cycle. It is carbon-free because it's nuclear energy-based. These systems are designed to be dry-cooled so that you're not tied to proximity with a body of water to get the water that you need for cooling. They just use the atmosphere as the ultimate heat sink, as we call it. It is a fully standardized reactor design, which is not expected to depend on the site. It is entirely factory built. You can see the scale here. It becomes transportable in a semi-standard ISO container. You see the scale there again in the figure here. It has standardized connections that essentially make it plug and play. So this system is expected to be online from the time that it arrives to the site in one piece to the time that it starts to generate either electricity, heat, or a combination of both in a matter of days or weeks. So vastly different time scales from traditional construction projects. Because of economic reasons, you cannot afford to have a large number of operators on site. The system is simple enough that can be basically designed to be semi-autonomous or fully autonomous with remote monitoring and very, very limited remote control. This is feasible and has been already demonstrated even in non-nuclear systems of much larger size and complexity than what we're talking about here. Very importantly, the reactor is not refueled on site the way that traditional large nuclear plants are refueled. But once the fuel runs out of energy or juice, if you wish, the whole thing is sent back to a centralized facility where the nuclear battery is refueled, refurbished, and then either sent back to the same site or to another site to serve a different customer. So what we have in mind here is, of course, is a fleet model where you have dozens, hundreds of these batteries, and it serves a number of customers. And it doesn't really matter which particular unit you get because they're all the same. Now, the implication of this offsite refueling is that the customer, the user, does not need or does not have a need for either on-site handling or storage or radioactive material. And again, we think that this is going to be important in terms of commercial acceptance as well as social acceptance. So all the fuel handling, both front end and back end, is done at a central facility dedicated for that purpose. Very, very important. The nuclear battery has a 2 orders of magnitude minimum lower footprint on a per unit energy generated than other low carbon alternatives. The image that you see here superimposes a 10 megawatt nominal wind turbine and 10 megawatt nominal solar panel field with their own capacity factor. So in fact, this would go up by a factor of 3 for solar, a factor of 2 for wind. And the little green rectangle that you see there is the physical footprint of a nuclear battery of equivalent capacity. And of course, with a nuclear reactor, you get dispatchability, so higher capacity factor. Also, what makes this technology attractive and in many ways different even from the small modular reactors and certainly different from the traditional large light water reactors is that Western suppliers are in the lead for the design and development of these technologies, whereas the center of gravity for more traditional nuclear, as I mentioned a few minutes ago, has definitely shifted to the east. Now, there is a number of vendors and nuclear reactor technology companies that are working on this. Some are established. You recognize certainly Westinghouse, a venerable player in the nuclear energy business. Also, Los Alamos and NASA have developed their nuclear batteries. Some are newcomers like Core Power that is developing a nuclear battery for ship propulsion, and then a couple of other smaller startups that you see here. Now, the idea of a portable microreactor is not entirely new. In fact, the US Army tested a couple of such portable microreactors back in the 1960s. What has really changed since then is that a whole suite of technologies that can be used now to design and develop and commercialize a 21st century nuclear battery have become mature since then. These are things like compact gas turbines or additive manufacturing, robotics, AI, advanced nuclear INC, nuclear materials, etc. And once again, what makes this palatable and attractive here in the US is that a lot of these technologies happen to be strengths in our country. And so there is sort of an incentive for using them also in this particular field. Lastly, there is a very strong synergistic effort with government. I mentioned private capital, but the government is not dormant on this particular technology. There are several programs by DOE, by DOD, Department of Defense, as well as NASA for space applications that provide a nice context, the test beds and capabilities and national labs that can be used for developing and testing these nuclear batteries. Now, so that's the small scale part that I advocate for. The second is the shorter testing and licensing. And what it really boils down to is the safety characteristics of these nuclear batteries. So in general, for any nuclear reactor, there are three basic safety functions that have to be achieved. The first is, in the case of an abnormal occurrence, you want to rapidly shut down the fission reaction and keep the reactor subcritical, as we say. Then you want to continue to adequately cool the nuclear fuel during shutdown. And lastly, you want to prevent the release of radioactivity into the biosphere under any credible circumstance. Now, there are inherent safety features for these nuclear batteries, as well as what we call passive safety systems, the combination of which allow you to achieve those safety functions with no external intervention. The inherent safety attributes that I'm referring to are, for example, the use of coolants in the core that do not boil off, or the use of fuel forms that are extremely robust in retaining the fission products, that's basically the bulk of the radioactivity within the core itself, or things like a high thermal capacity of the core, which allows you to absorb a lot of heat without enhancing temperature, as well as safety systems that rely on natural circulation or pressure drops or things of that type, or radiative heat transfer, no moving parts and no need for pumps and diesel generators and things of that type. So if you combine these two features, then you can basically achieve those safety functions with no external intervention. The implication of this is that accidents like 3 Mile Island, Chernobyl, and Fukushima are really eliminated by design. It just cannot basically occur. And very, very important also is that the so-called emergency planning zone is limited to site boundaries. So even under the worst possible scenarios, people living surrounding the power plant or the nuclear battery would not need to evacuate or take any action. And again, that's very important for the social acceptance and the social adoption of this technology. Now, this is not just sort of theory. This shift in testing and licensing paradigm has been actually tested by NASA and Los Alamos for their space nuclear battery, which was designed, fabricated, and tested between 2015 and 2018 in a little bit less than 3 years, which is unheard of for new nuclear technology, and for a little bit less than $20 million. So very, very low cost. Now, they leverage substantially the capabilities in the DOE, Department of Energy complex, but those capabilities are available also for the commercial nuclear batteries that I'm focusing my presentation on. Now, the third element of that shift in paradigm is the higher added value of the energy product that these nuclear batteries can provide. Now, higher added value for any energy technology could come from a policy signal. In the case of nuclear, that would need to recognize the non-emitting nature, the good economic impact, and the contribution to energy security and resilience that nuclear electricity can provide. When I gave this presentation, a year ago, I would say unlikely and beyond our control. Now, with the change in administration, I would say it's possible. There is certainly some serious commitment now in decarbonizing the electric grid, but it still remains beyond our control for sure. Or the alternative, or I should say in parallel, the idea here is to capture new markets in which nuclear products could sell at a premium. And with the right technology, I think those markets are within reach. So I said this at the beginning, but it's important to sort of remind ourselves that even if you do a 100% decarbonization of the power sector, that's 25% of the total emissions. 75% of the emissions come from sectors like factories, industry, manufacturing, transportation, buildings, and agriculture. Now, some part of those sectors can be electrified, but not all of them can. And in some cases, electrification would be very, very costly. So we need to focus on all these sectors and not just the power grid. So that's where the nuclear batteries can play a big role, because effectively they can provide heat, electricity, or a combination of both to every sector of the economy, whether you are connected to the grid or in the proximity of the grid or far out. The co-location of nuclear batteries, which are very, very compact and they're not geographically constrained, with these end users could provide the energy that all these applications require, and it would be carbon-free. So examples, desalination plants or pumps for flood protection. We're going to need a lot of that as rising sea levels are becoming a reality. Hydrogen electrolyzers, wherever they're found, even locally, if you want to produce hydrogen for local vehicles without big storage and transmission, you can do that with batteries. Data centers, indoor aquaculture, so food or containerized farming, freight ship propulsion, even portable pharmaceuticals. And then, excuse me, the big potential game changer is heat, which not a lot of people talk about, but it's actually a much bigger market than electricity. And a lot of factories need, yes, power, but they need a lot more heat than they need power. And currently they're burning natural gas, whether there are chemical plants or food processing facilities, et cetera. They're going to need a combination of both. And again, nuclear batteries can play a role there. District heating, microgrids of every type, remote communities, mining sites, military bases. I mentioned space, of course, that's not going to be a big market, and indoor farming already. The collocation of these microreactors or nuclear batteries with the end users eliminates the need for massive, costly, and as we've heard in the previous presentation, often unreliable infrastructures for energy storage, transmission, and distribution. So the potential, we think, is very high. So in order for this to happen, well, there are many things that have to happen, but clearly this technology has to be cost competitive. So what we did in our analysis, we first asked ourselves, what are going to be the cost targets for heat and electricity in these markets that we're interested in? So let's start with heat. For heat, the main competition currently is natural gas-fired boilers. Now, natural gas boilers tend to be too small for carbon capture and sequestration, so burning that natural gas in these boilers will incur some kind of carbon price or carbon penalty in a carbon-constrained world. So what is shown here is the cost of heat, which does not include the cost of the boiler, so this is just the cost of the fuel produced by natural gas as a function of natural gas price for different carbon taxes. And you look at a reasonable range here, the cost target for a nuclear battery that wants to compete against natural gas here would be of the order of $6 to $15 per million BTU. You can see the equivalent there in megawatt hour. Those are megawatt hour thermal, of course. For electricity, the idea here is that you're going to compete against dispatchable electricity. At the moment, dispatchable electricity really means natural gas with carbon capture. The solar and wind plus batteries in terms of cost are going to be much higher than what we see here. And so we looked at the moment for natural gas and with carbon capture. And here, whether it's distributed generation or it's on the grid, it makes a little bit of a difference. Whether you put a carbon tax or not on the residual emissions also makes a difference. And so if you look at a range, we think that nuclear batteries that could produce electricity co-located with the end users in the range between $70 and $115 per megawatt hour would be quite competitive for those markets. So those are the cost targets. And then we said, okay, do we have a fighting chance here? We need to sort of delve a little bit deeper into what these nuclear batteries are going to look like, make some assumptions about the cost and the design features of these nuclear batteries, and try to estimate what is the levelized cost of electricity, and importantly, the levelized cost of heat, and compare these estimates with those cost targets. So I'm not going to go over this table, but you can see sort of the number of parameters that we need to specify. These are things like, of course, the electric power output of a single unit. What is the thermal efficiency? What is the refueling interval? What's the capacity factor? For how long is it going to stay down for refueling and servicing? Fuel enrichment, discharge burnup, cost of uranium feed, conversion, the number of FTEs, the number of operators that you have, on site, the compensation, and then economic lifetime, cost of decommissioning, discount rate, et cetera, et cetera, et cetera. So all these things, if you're interested, there is a paper that we published in Energies less than a month ago, and you can see all the assumptions that we made and justification for those assumptions. Now you then calculate your levelized cost of electricity or your levelized cost of heat, very straightforward. You have to annualize fuel, operation and maintenance and capital costs, and then at the denominator, if it's electric power, if it's cost of heat, electricity, you get electric power. If the cost of heat is the thermal power. And you get a point result for LCOE and LCOH. And it turns out that these point results, or sort of these baselines, are well within the range that we're interested in. So that's encouraging. But of course, you have to recognize that the uncertainty in the assumptions that we made are massive. And so what we did next was a parametric study, if you wish, a sensitivity study, to see what are really the cost drivers. And if some of these cost drivers deviate significantly from the baseline level, how does that affect the levelized cost of electricity and the levelized cost of heat? So we look at 8 or 9 parameters, which are shown here, ranges. So power output between 1 and 20 megawatt, that's a big range. Fuel enrichment between 5 and 20%. All this qualifies as low enriched uranium, so with minimal proliferation concerns. Discharge burnup is the amount of energy extracted per unit mass of the fuel. Refueling interval is how long it takes between one and the next refueling outage, if you will. The fabrication cost, very important, excluding the fuel, between $1,000 and $10,000 per kilowatt. Again, that's a big range. The number of FTEs for operation and maintenance, discount rate, and capacity factor. Now, I'm going to spare you the long list of plots here that show the different trends and the sensitivity of this. I'm just going to show you, in the interest of time, one that is particularly meaningful. As you would expect for all nuclear systems, the capital cost, or the fabrication cost of the machine, is very important. And for nuclear batteries, this is no exception. So what is shown here is the LCOE, dollars per megawatt hour, as a function of the fabrication cost for the battery. So our baseline is $3,000, which we've justified with the bottom-up cost estimates. And I'm going to mention the analogy there with jet engines in a minute. But if you look, of course, at this plot, now you see that as you increase the capital cost, well, fuel and operation and maintenance costs don't change, but the levelized cost of electricity does change quite dramatically and linearly with capital, because that's sort of the biggest, the biggest piece. Now, the realism of $3,000 per kilowatt, our baseline power output is about 10 megawatts. So that means $30 million for the construction of the machine, excluding the fuel. Is that high? Is that low? So if you take a jet engine, which you can think of as a mini power plant, a large jet engine generates about 50 megawatt of mechanical power at takeoff. Of course, that mechanical power is that turned into thrust, which allows for the aircraft to take off and then stay airborne. That machine cost about $25 million. It's a very delicate, complex machines. In fact, in some respects, more delicate and more complex than the nuclear batteries that we're talking about. And at $25 million, it's about $500 per kilowatt. Now, the analogy is not perfect, but this is sort of to give you an order of magnitude. This is not unrealistic to assume that a 10 megawatt nuclear battery will cost about $30 million to fabricate. And we have a bottom-up, quite detailed calculation that shows that that's realistic. So we, part of the sensitivity analysis, we also wanted to see if I take the principal cost drivers and put the worst case scenario in, how is the levelized cost of electricity going to change? And not surprisingly, of course, it's going to change quite a bit. So this is a notional example of an expensive design. This deviates significantly for our baseline in both fuel operation and maintenance and capital cost. And so if our baseline levelized cost of electricity was at the order of $80 per megawatt hour, and therefore quite competitive if realized in all those markets, this nominally expensive microreactor nuclear battery would be about $300 per megawatt hour, which is, of course, a lot less attractive. Now, there are many applications, off-grid applications, particularly remote communities, mining sites, where even at $300 per megawatt hour, which is 30 cents per kilowatt hour, you could be competitive. So that doesn't mean there is no market. If you are at that high cost, it means, of course, the markets are much smaller. So with that, let me close. The takeaway messages is that these portable microreactors, which we've been calling nuclear batteries, have the potential to provide on demand, that's dispatchable because that's nuclear, carbon-free, potentially economical, certainly resilient and safe energy for distributed heat and electricity applications. Very important, as I've been beating you on the head in every sector of the economy, not just the power grid. The cost targets are shown there. We think they're quite reasonable, and it appears that the nuclear batteries can't meet those targets, depending on the assumptions, quite comfortably, but there are some cost drivers that we need to pay attention to. Power output has to be maximized within what we call net nuclear battery constraints. So the size has to remain such that you can do truck transportability. You have to be able to remove the decay heat in a passive fashion. The staffing has to be limited to that range between 0.5 and 1.5 FTE per megawatt. These results come out of all those plots that I skipped in the interest of time. Enrichment less than 10%, burn up greater than 10 megawatt. Nuclear battery fabrication cost, that's the big one. If it's less than $5,000 per kilowatt, then you have potentially a very, very attractive product. And then lastly, we did not find any cost incentive for very long refueling intervals. Some vendors are looking at 20 years without refueling. There might be other considerations that drive that design that makes it attractive. The fact that you don't have to sort of change out the nuclear batteries frequently, but in terms of just levelized cost of electricity, we didn't find that to be particularly compelling. So I'm going to leave you with this slide, which is somewhat provocative. At the top is the traditional, this is the present, the past, beautiful large nuclear power plants connected to the grid. That site is when the third unit is going to be operational. Who knows when. It's going to be 5,000 megawatt of electricity, very reliable, and is going to go on for 60 years. But it's taking forever to build, and it costs a fortune. So maybe the future for nuclear looks also like what is shown here at the bottom, much, much smaller, more nimble, lower capital, lower financial risk. So, Audin, with that, let me stop here, and I'm happy to take questions that might come from the audience or from you and the other panelists.
Right, thank you so much, Jacopo. Fascinating overview of the nuclear battery concept, which could certainly play a major role in the decarbonization challenge. For instance, as the firm and flexible resource that Tyler was talking about in the previous presentation. So we have a few questions in the Q&A box already. Please add to those questions, everyone. So I'll go right to the first question here, and that's from Rob Hayes from NC State. He has an elaborate question here, but he brings up the Fukushima accident, and he states that there were no statistically significant medical effects and refers to reports from the UN and WHO. And he argues that this experience needs to be brought up when we talk about nuclear, and he asks, shouldn't we discuss these facts when talking about nuclear? So Jacopo, do you have any comments?
Well, my comment is that lines? I think that's that's a good point. I am familiar with the UN report, which quite conclusively states that there are no long-term public health consequences of Fukushima. And so that's sort of the science, that's a fact, and that's all good. But from a practical point of view, for widespread adoption of nuclear energy, I think that class of accidents where there is a significant release of radioactivity into the biosphere with potential consequence of evacuation of the local population are not going to be acceptable going forward. And so this is I think a burden for the nuclear industry to come up with designs and systems that do not have those consequences, even under the worst case scenarios. And I have to say that I focus on nuclear batteries. Certainly, the nuclear batteries are expected to meet those objectives, but even the small modular reactors, the so-called Generation 4 systems, they all basically eliminate this class of accidents by design. So I think that message has been heard and is being integrated in the new technologies. That's all good. I think it makes it more robust and hopefully and ultimately more socially acceptable.
Great, thank you. So let's go to the question from Eduardo Fernando Mello. He brings up an interesting perspective, from the manufacturing or manufacturer perspective, he asks what can be done about the risk of the manufacturer of these nuclear batteries going bankrupt. How would the client have any security that he will not be stuck with the nuclear waste?
Okay, so I think there are two elements to this question. The first is what is the uncertainty about maybe manufacturing or fabrication capabilities, and the second is more focus on nuclear waste, if I understand the question correctly. So on the first element, ultimately, in order to realize very low fabrication costs, you're going to need factories that are dedicated and optimized to the production of these nuclear batteries. However, this is the classic chicken and egg problem. You cannot afford to invest, I don't know, hundreds of millions of dollars in a new factory until you have an established book or order book for these nuclear batteries. And you're not going to have an established order book until you're shown that your cost is going to be low. So this is going to have to go in smaller steps. And we have surveyed the existing nuclear manufacturing capabilities in the United States and globally, but the focus here is the US, and we and not just we in my group, but others have concluded that there is enough capacity and capabilities to build the first few units in the US. And if those first few units are successful, and what does that mean to be successful? Well, the first demonstration is going to be at a national lab. And success there is going to be measured in terms of proving the performance, the technical or safety performance of the system. The following units is going to be commercial deployment, and their success is going to be, well, is it cost competitive? Now, realistically, that first commercial unit will not be in a market where the cost target is going to be very aggressive. It's likely going to be a military base or a remote mining site or something like that, where you're competing against, $300 or $400 per megawatt hour. Once you have those first few units out of the way, I think confidence is established, and the manufacturers will have an incentive to invest in their own factories to make them more and more optimized for serial manufacturing of these units. The second part of the question is about waste, and we don't envision that the fabricators, the manufacturing, would also manage the fleet. So the model that people are looking at for these nuclear batteries is where you have a company that manages the fleet. So it procures the nuclear batteries from fabricators, it procures the fuel from fuel vendors, and we have many established nuclear fuel vendors in the US and around the world. And then this company obviously has to own that central facility where the nuclear batteries are refueled and refurbished and then sent back to the customers. So the risk to the fabricators is associated with the handling of a high-level waste is non-existent, because they're not really part of that process. I hope that answer. It was a long answer, but it was an interesting question with multi-parts.
Mm-hmm. Yeah, and a very interesting answer as well. The next question, it's Jaming Khan who asks, are the nuclear batteries able to change the output fast enough to fit the system with a large share of renewables? And that's a question that I relate to. And if I may add a little bit, so as you know, wind and solar very rapidly. How fast can you ramp such a battery up and down, and can you actually shut it off entirely for a while and then bring it back up at some point later?
Yeah, that's a good question. Let me take a step back and say that contrary to widespread popular belief, even traditional large-scale nuclear power plants can and do follow the load. They do that on a daily basis in the US Midwest because of the high penetration of wind. They've been doing it for 30 years in places like France, where actually the nuclear capacity is the majority of the grid, and so there is a need for some flexibility in some of these plants. When I say that they follow the load, those traditional plants, plus or minus 50% in power, 50, in half an hour. Now that's not fast switch. So if you have much faster variability, you still need the peaker turbines, gas turbines, and things of that type. So that's the traditional plants. All these new plants are designed for even more aggressive load following. The nuclear batteries to give you the honest answer is we don't know yet how fast they can go. I doubt that they would be able to go instantaneously within seconds from 0 to 100, although I point out that naval reactors that are used for propulsion of submarines and aircraft carriers do go from 0 to 100 in literally seconds, but they are different design, different robustness, different requirements. But nuclear batteries certainly will be able to follow the load and follow the load fast, but maybe not fast switch. Now, let me close the answer by saying that I hope that I convey the idea that this is not meant to be grid connected. Maybe it will, if the cost comes down to the point where it can compete with other low carbon energy technologies on the grid, it makes sense to also connect these nuclear batteries on the grid. But otherwise, this is really to provide co-located, distributed local energy to things like microgrids or even isolated end users. And so if that end user needs a variable energy supply, these systems are certainly going to be able to provide.
That's a very interesting discussion. Let's do one more question, then we'll move on to the next speaker. And the question is, how soon do you think the technology would be adopted by industry? So in the US context, as you know, there are very ambitious climate goals under the current administration, for as soon as 2035. Could this play a role in that time frame, let's say?
Yeah, very good question. And the answer is absolutely yes. This is one of the most attractive features of the technologies because of the scale, the simplicity, and in many cases, the use of technology that does not require extensive R&D. The demonstration and deployment schedules here are very aggressive. So the very first application is going to be for the Department of Defense. The U.S. Army is going to come is sponsoring the the development of two designs in parallel, one by BWXT, that's one company, and the other one by X Energy. And they're planning the first demonstration in 2023, so a year and a half or so from now, and the deployment in the field by 2027. That's for the DoD application. In parallel, the commercial applications are on a little bit more dilute schedule, but not by much, with a 2026, 2027 commercial and a demonstration at the national lab 2025, 2026. So again, those scales are entirely compatible with the 2030, 2035 for sure vision or requirements that we're talking about. Now, my personal opinion is that given even the recent IPCC report, 2035 might not even be enough. We probably need all these low carbon energy technologies, whether it's wind, solar, storage, nuclear, much sooner than that. So yeah, great question. I think this is this is a selling point for these technologies, that you're no longer into a decade plus long R&D and development programs. This can happen very quickly.
Right, that's really what we need to address